looking at the splitting of d-orbitals. We're going to be looking at how this explains or gives us information about the colour of transition metals and why, whether the light that's seen as relevant to UV or visible spectrum also affects on whether or not we see a colour. So we already know from the atomic orbital section that we've got 5 d-orbitals: dxy, dxz, dyz, dx squared y squared, and dz squared. Now we also know that these orbitals are degenerate. Now there are occasions when they're not, okay? And that is to do with the approach of ligands. So in some complex transition metals, what we find is the d-orbitals are split. It's usually 2 are of a higher energy level than the other 3. As they're split in terms of the energy amount, they are no longer degenerate. The reason that this happens is because when the approaching ligands approach the electrons along the axis, what will happen is they'll start to repel each other. Okay, and as this happens, if you've got your repulsions, what will happen is the electrons will move to a different level. That's the electrons in the transition metal. Okay, so basically, as they're coming along the axes, it's going to be the x-axis, the y-axis, and the z-axis. The orbitals are affected by the dx squared, y squared, and the dz squared. This is because xy, yz, and xz, the orbitals are between the axes, are not actually lying along them. If you need to review, and you may want to do this anyway, have a look back at the position of all the orbitals and where they lie on the axis. Okay, but if they approach along the axis, as we said they do, it's your x squared, y squared, and your z squared that are affected. So what will happen is these 2 subshells will be raised to a higher energy level than dxy, dyz, and dxz. Now, we have we have a range, I was going to say 2 different classes, but we have a range of ligands. Some of them are classed as strong field ligands. At the other end of the spectrum, we've got weak field ligands. So it's like a spectrum, rather, would have been a better way of phrasing it, from one end to the other. So you've got your strong field ligands, and as we go along, that decreases till we get to the weak field ligand. This information is important, as you will see as we go through this section. So different ligands will have a different effect on the repulsion to the electrons. And because of this, we have different energy gaps. So not every ligand will cause the difference between the xy, xz, zx, and x squared, y squared, and z squared to be the same. The energy value can be different. Okay? Now, what we find is the ones that give us the biggest energy difference between the orbitals are going to be the strong field ligand. Okay, strong field, biggest difference. The weak field ones will therefore cause the smallest energy difference between the subshells. We can put the ligands, or not just can, the ligands are put into an order of their ability to split the d-orbitals. Okay, this is known as spectrochemical series. Now, we don't need to know the order. You yourselves may have noticed in the past paper questions, it gave you examples. Okay, so one end of our spectrum, we've got iodide ions, and the other, we've got cyanide ions. We've got fluorine ion, or fluoride ions rather, in the middle, water slightly to the right of fluoride, but it's certainly got less splitting effect than ammonia or cyanide ions. Okay, it says large orbital splitting. That's just thinking about how big the gap would be between the 2 sets of orbitals. Small orbital splitting to try and ingrain into our brains that it's a much smaller gap there. Okay, weak field is going to be small, strong is going to be large. So I suppose we could think about it, someone who's really strong trying to push 10 kilograms, they'll be able to push it no problem. Someone who's really weak trying to push 10 kilograms, they're hardly going to be able to move it. So the gap there from where they were initially stood is going to be tiny. I don't know if that helps or not. this introduction about why transition metals are coloured does start to lead into catalysis, which is the next bit we're going on to. Okay, it's in the next PowerPoint. So we quite often find our transition metal complex and ions are coloured. Think about manganese ions. They're the purple ones you'll have come across. Okay. Now, there are reasons for this. We already know that if light is absorbed, when electrons in the lower energy level will promote, we will begin to see or could begin to see colour. Okay, we have to be very careful how we phrase all this colour thing, all this colour information, as when we're asked in the spectrochemical series and when we're asked in transition metals, and also we're going to meet it again when we look at Unit 2, because we can get some organic substances that are coloured. There have to be specific reasons for each one to get the mark. If you mix them up, you won't get the marks. So for this one, we're saying for transition metals, we've got light being absorbed when the electrons are in the lower energy d-orbital and then promoted to the higher energy d-orbital. We're not talking about why, we're just saying that they can. For this to happen, it's a d-d transition. They're moving from one d-orbital to another, hence d-d, and they're transitioning from one level to the other. Okay? We have to remember that whatever colour we see is complementary to what was observed. Right, so it's page 20 of the data book you'd want to look at for your colours. Now we're saying that we see the complementary colour. So permanganate, we normally see it as purple. That means the wavelight that is being absorbed is is the corresponding wavelength to that. So it would be green that's being absorbed, and the wavelength would be between 560 nanometers and 500 nanometers. Okay. If it had been blue would seem, it would mean that yellow was being absorbed, so it'd be between 595 nanometers and 580 nanometers. Okay. Right. Now, I said a few minutes ago that it was extremely important that we were very careful how we refer to colours depending on what part of the syllabus we're looking at. Okay? It's a slightly different reason because we look at energy or photons being emitted when we're looking at spectrochemistry. There are substances in organic chemistry, and I don't want to go into that in detail, but there's something that happens there that'll give colour, and if you get it wrong there and go on about promoting electrons or anything like that, you will lose the mark. Okay, so when we're talking about transition metal complexes being coloured, we need to look at what's happening. And it says we must remember to refer to the colour coming from the energy corresponding to the electron transition to a higher energy level. So what we're saying here is in this d-d transition, we've got the 3 at the bottom, and the electron has been promoted from one of the 3 at the bottom up to your z squared or your dx squared y squared orbital. Okay, so the colour comes about from being promoted to the higher orbital. We also have to look and see what part of the spectrum it's in. The only time we will be able to see colour is if it's in the visible spectrum. Now, d-d transitions can also happen in the ultraviolet spectrum. If they do happen in the ultraviolet spectrum, or the wavelength that's there is the ultraviolet spectrum, it'll look colourless to us, and that is because our eyes do not detect that colour.